I'm really sorry for that. So let me start again. Okay. So, uh, hello everyone. So welcome to today's session uh, of basic real analysis. Today we will discuss some questions on sequences and topology of real number line. Okay. So this is our third session in this course, basic real analysis. So let me introduce myself. I am Prerak Deep from Aizer Bhopal. I am conducting these weekly discussion session of 2 hours regularly. Uh, and recording of these sessions are available on the YouTube channel named Maths with Prerak Deep. So you can search this channel in the YouTube search box and you will be able to find these recorded sessions of mine. Okay, so today I will be discussing problems on sequences first, and then in the latter half I will be discussing problems on topology of real number line. So before starting discussing problems on sequences, let us first recall what sequence is. So a sequence xn on a set A is a function from natural number sets to that set A. We denote this function xn to be x subscript n, and moreover we denote a sequence to be a curly bracket xn, where n is bearing over n. And for those who don't know what this symbol n represents, it is nothing but the set of all natural numbers. And what are natural numbers? So 1, 2, 3, 4, 5, 6, and so on and so forth are called the natural numbers. Okay. So throughout our discussion, I will be assuming that my set on which I am defining the sequences is nothing but R. Okay. So this denotes the set of all real numbers. Okay. Now let's move on to discuss the first problem. Okay. So in this first problem, we have given four sequences, and you need to find out the formula for the nth term of each of the sequence. Okay, sorry, so we have given us sequence nth term, and you need to determine the first five terms of this sequence. So it's a very simple exercise. You just need to put values of n in order to determine the all five terms, first five terms of it. So I will start with with a. So a is xn is given to be 1 plus minus 1 to the power n, correct? Okay, so now first five term, if when n equal to 1, it is 1 plus minus 1, which is 0. N equal to 2, it is 1 plus minus 1 square, which is going to be 1 plus 1, which is 2. N equal to 3, it is going to be 1 plus minus 1 to the power cube, is going to be 1 minus 1, 0. 4, it is going to be again 2, and for 5, it is going to be again 0. So we can notice one thing from this, that on even terms, which is these, sorry, on um, odd terms of sequence xn are 0, and even terms of sequence are 2. Okay, so this is just a observation that we can deduce from this, understanding this, these five terms of first five terms of the sequence. Okay, now what is the second sequence? Second sequence is given to be minus 1 to the power n divided by n. Okay, so let's find out the first. So second sequence is minus 1 to the power n divided by n. Correct. So when n equal to 1, it is minus 1 to the divided by 1, which is minus 1. N equal to 2, it is minus 1 square by 1, which is 1. N equal to sorry, divided by 2, so it will be 1 half. Okay, n equal to 2 will be half. N equal to 3 will be minus 1 over 3. 4, it will be 1 over 4. N equal to 5, it will be. So you can notice, because of this term, this term in the numerator, uh, you can see that the odd terms are getting negative sign and the even terms are getting positive sign. Okay, and because of 1 over n term, you are getting the whichever term you are computing, that is coming in the denominator. So yeah, so this will be a sequence. Okay, these are the 5 terms of the sequence. And if you know, if you have seen my last discussion, so you know what a convergent sequence means. So this is a convergent sequence. Okay, um, and I leave it to you guys to prove that this is a convergent sequence converging to 0. Okay, so I leave it to you to prove. I have proven the similar exercise in the last discussion session. So our sequence converges to 0. Okay, so to prove that. Okay, okay, so now let's move on to discussing the third sequence, which is 1 over n times n plus 1. So it is given to be 1 over n times n plus 1. So this is the C part. So for n equal to 1, I get it is 1 times 1 plus 1, which is 2, 1 over 2. N equal to 2, it is 1, 2 plus 1, which is 6. N equal to 3, it is 3 times 4, which is going to be 12. N equal to 4, it is going to be 4 times 4 plus 1 is going to be 20. And n equal to 5, it is going to be 1 over 5 times 6, which is 30. Okay, so now you can also see that this sequence is also as n tends to infinity. Okay, as n is increasing, as n is increasing. Okay, as n increasing, you can see that this term, the sequence is also tending towards to 0. Okay, it is getting, the denominator is getting larger and larger as n is increasing. So when n is very large, so the denominator is also going to be very large. That means 1 over that denominator will be very small value, so it will be very close to 0. So it will be converging to 0. Okay, so so in some sense, if you can compute the first 5 terms of a sequence or first 6 terms of a sequence, you know, you can understand the nature of the sequence, whether it is converging sequence, and if it is converging, where it happens to converge. Okay, you can see a pattern out of it if you calculate, if you compute the first 5 terms or 6 terms of that sequence. So that's one of the benefit of computing the first 5 or 6 terms of the sequence. Second, you can understand that whether this sequence is, the pattern of the sequence, whether it is divergent sequence or it is convergent sequence, something like this you can also understand from this. Okay, so these are a few benefits uh, uh, you can just you can get by just writing down the sequences first few terms. Okay, now let's move on to the last sequence, which is 1 over n square by plus 2. So 1 over n square plus 2. Okay. So n equal to 1, it is 1 over 1 plus 2, 1 over 3. N equal to 2, it is 4 plus 2, 6, 3, 9 plus 2, 11, 4, 16 plus 2, 1 over 18, and 5, it is going to be 1 over 27. So again, you can see as n is increasing to 0, infinity, this sequence is also, the denominator of the sequence is increasing very fast, so it is also tending to 0. So this is also a convergent sequence. This is also an example of a convergent sequence, and you can also guess the limit of the sequence. It is 0. Okay, so there is a mathematical way to prove this also, uh, which you need to do in order to prove that the sequence converges to 0. We will also see that kind of proofs in today's discussion. Uh, yeah, so what we have noticed that on except the first sequence, all the other three sequences are convergent. The first sequence is not convergent sequence. Uh, the first sequence is actually a divergent sequence because it is, so on the odd it is taking value 0, and on the even it is taking value 2. So it is a jumping from 0 to 2 and 2, between 0 and 2. So it is jumping between these two values. So it is not converging to any point. Okay, um, so that's why it is not a convergent sequence, a divergent sequence. Okay, so now let's move on to this question. So let me improve this question by dividing it by n. Okay, um, now let's look into this question. So this question asks you to find out the limit of this particular uh, sequence, you can say. Okay, why you can think of it as a sequence? Because you can define your sequence to be, you can define your sequence to be this, for each n in natural number. Okay, so this is how you can define it, your sequence. And what do we mean by limit of xn? It will mean the same limit of, okay, and when n tends to infinity. So what does it mean that, so when you are asked to find out limit of a sequence, so under the assumption, so you are, so in the question it is already been assumed that the sequence is convergent. Okay, so I repeat, so whenever you are asked to find out a limit of a sequence, so it has already been assumed that that sequence is convergent. Okay, that's why you have been asked to find out the limit of the sequence. And what do we mean by limit of a sequence? It is the point or a number on which this sequence converges. Okay, so we work with this sequence. Okay, uh, so since it is already given, it is already asking you to find out the limit, so you say it is a convergent sequence. And now we use a definition of a convergent sequence. So in other words, uh, we say xn is convergent to some x. Okay, so we say xn, so I'm just, it's convergent to some x as n tends to 0, infinity, uh, if for every epsilon, or for any epsilon, for any real value epsilon, there exists some, there exists a natural number n such that xn minus x must be smaller than 0 for all n greater than or equal to that capital N. Okay, so in our case, what is the value given? So it is given to be 0. So the limit is given to be 0. In other words, your sequence xn is converging to 0. So in our case, x is given to be this, xn is given to be this sequence. Okay, so you start with some epsilon. You start with this assumption. you start with this assumption that for some epsilon there some for some epsilon this thing is happening. Now you want to you extract that information what n will it be happening. Okay, so yeah, so if you do that you will get n square plus 1 square root minus n by n minus 0. This whole thing is nothing but equal to this thing. Okay, now in this expression you can always take n out. Okay, you can take n out. So in the first term you take n square out, so it will, and then you perform the square root on it, so you will get n out, and inside it will be 1 over 1 plus n square minus n divided by n. Okay, now further, if you, now you can divide n, so you will get uh, 1 plus 1 over n square minus 1 modulus of this. Okay, so now we come back to this part that so you have this expression, so you have reduced your sequence into this thing. Now this expression is smaller than the square root of this. Okay, and this thing is smaller than 1 plus um, yeah, so what I meant is that this thing is smaller than 1 over n square, square root of this, and this thing is nothing but 1 over n. So yeah, so and we know that this is and we can use the bound of 1 over n to say that, yeah, now we can use the bound of 1 over n to say that this is smaller than epsilon. So we know that for this sequence there exists some n in natural number such that this whole thing, this 1 over n, is bounded by epsilon. So we can use that epsilon to bound this sequence as well. Okay, so this completes the proof of this part. Okay, so now we move on to discussing this problem, limit sine n over n. Okay, yeah. So what is this sequence? So we will use the squeezing lemma in order to prove that this limit of this sequence is not is zero. So what is squeezing lemma? Is basically you try to sandwich your sequence from some upper bound sequence and some lower bound sequence, and you know the limit of the upper bound sequence, some upper bound sequence and the lower bound sequence, and if they converge to the same thing, then this sequence also converts to that value. Okay, so okay, I will explain this bound in the end of the session. Okay, how did I get this? If it's wrong, then I will also point it out. I'm not sure right now, so I will discuss it later. Okay, so now let's move on to discussing this problem. So here we will use a result called the sandwich theorem. Okay, so sandwich theorem says that you need to bound your sequence by known sequences. Okay, so if xn be a real sequence, and let xn be a real sequence, and xn is bounded by some wn and zn for each n in natural number where the sequence zn and wn are convergent converges to x as n tends to infinity, then this sequence then xn also converges to x as n tends to infinity. Okay, so we will use this theorem in order to prove this. So first I will prove this result, and then we will prove the theorem. Okay, so since it is sequence is given to be sin n over n, this is your sequence xn. Okay, we define it to be the xn. Now we know that sin n has some property that it is sin always takes value between -1 and interval -1 and +1. So this always belongs to interval -1 +1. Okay, so what does it mean? It means that sin n is always lower bounded by -1 and upper bounded by +1. Okay, so in this case, now if I divide this sin n by n, I will get -1 over n and 1 over n. Okay, so now where does it lead us to? So I will get two sequences. So I have gotten a bound upper bound sequence and a lower bound sequence. So what is my upper bound sequence? So what is upper bound sequence is wn. So our wn is 1 over n, and lower bound sequence is -1 over 1 over n. Okay, so I have gotten two sequences, 1 over n and -1 over n. Now so the hypothesis is being satisfied. So what is the hypothesis? Hypothesis is wn is bounded by, so we assume let this thing, so the hypothesis is satisfied. Okay, now uh, do we know the limits of wn and zn? Yes, we do know the limit of wn and zn. So where do they converge? So wn, which is 1 over n, it converges to 0 as n tends to infinity. Okay, and similarly zn, which is 1 over n, which is -1 over n, is also converges to 0 as n tends to infinity. Okay, so uh, yeah, now we use the sandwich theorem. So what does the sandwich theorem says? That if I have a sequence sandwich between two sequences whose limits are same, okay, then the sequence also, then my original sequence also converges to the same number. So this implies, so by sandwich theorem, xn also converges to 0 as n tends to infinity. So this proves the limit of sin n over n is 0. Okay, now let's move on to the understanding proof of the theorem. So we have given um, lower bound sequence and upper bound sequence bounding xn for each n in natural number. Okay, So, and we also know that, so this is the first thing given, and Zn and Wn both converges to X. So that means for given epsilon, we can find out a natural number n1 in natural number and natural number n2 in this, such that xn minus x is smaller than epsilon for all n greater than equal to n1, number 1, and wn minus x smaller than epsilon for all n greater than equal to n2, number 2. Okay, now either n1 will be greater than n2 or otherwise. Okay, so we define n to be the maximum of n1 and 2. Okay, now for maximum, both of the first and second will satisfy. So for n, 1 and 2 are both satisfied. Okay, so now what do we need to do? We can just take, um, yeah. So yeah. So now we just move on to now this part. Because xn is bounded above by wn, I think so, zn, or wn, and bounded below by zn. So yeah. So zn minus x, if I subtract it out, x, then the inequality won't gonna change. It's not gonna change. Inequality is not going to be changed. Okay. Now further, we know that zn minus x modulus of this is smaller than epsilon. Okay. So what does this mean? This is same as that it is bounded below by minus epsilon and bounded above by epsilon. Similarly, wn minus x is smaller than epsilon is equivalent to say that wn minus x is bounded below by minus epsilon and bounded above by epsilon. Okay, so for epsilon, we have found out n, which was nothing but the maximum of n1 and n2 belonging to natural number, such that um, now we use this a and these two equations. Okay, so from a and b, we get xn minus x is, which is smaller than wn minus x, and now wn minus x is smaller than epsilon, and xn minus x, which is larger than zn minus x, which is larger than minus epsilon, we get that xn minus x is, the modulus of that is smaller than epsilon for all n greater than equal to n. Okay, so this completes the proof, and which this completes the proof of the sandwich theorem. This last line implies that xn converges to x as n tends to infinity. So this completes the proof of the sandwich theorem, and we have used the sandwich theorem in order to calculate the limit of sin n by n. Okay, I hope this is clear. Okay, now we move on to discuss limit of few more sequences. The first sequence, let's look into this. So we have first sequence, which is we need to find out the limit of 2 plus 1 over n square of this whole thing. Okay, now we use here multiple facts. So first fact is that number one, and I have discussed the proof of these facts in my previous discussion session, so I'm not going to repeat these proofs, but I'm going to state the facts, state them as a fact. Okay, so first fact is that sum or difference of two convergent sequences is again a convergent sequence. Okay, so that's what I'm going to use in this proof, in this question. So we all know the formula for a plus b whole square. Okay, so this expression whose limit we need to find out can be written down as this. Okay, so you can see that this one sequence becomes sum of three sequences. Okay, first sequence is a constant sequence 4, second sequence is 1 over n square, third sequence is 2 over n. Okay, so in other words, if I am finding out the limit of this sequence, then it is same as finding out the limit of individual three sequences and then summing them up. Okay, so this also gives me formula. The first fact also gives me the formula for the uh, sum of the sequences. So the limit of the convergent sequences, the limit of the sum of convergent sequences is nothing but the sum of their limits. Okay, so I can break it into this limit of the constant sequence 4, limit of 1 over n square plus limit of 2 over n. Okay, now again yeah, so now what is limit of 4? So 4 is a constant sequence, so constant sequence on always converges to itself. So limit of this will be 4. What is 1 over n square? So limit of 1 over n square is what? So answer is 0. It's going to be 0. How do we prove that? So we can again go back to this thing. So we claim that it is 0. So for epsilon, we need to find out some n for which this is going to always happen. Now we can, now this 1 over n square is smaller than 1 over n. Okay. And we know that 1 over n converges to 0. So for this, we can always find out some capital N for which this value is smaller than epsilon for that epsilon. Okay, so we can find out this. We can also prove that this is convergent. So in other words, limit 1 over n square is equal to 0. So this is fact number 2. I have given proof of that also. And number 3, because and number 3 is again simple because 1 over n is 0. So this is 0. This part is also 0. So limit of this whole thing is 4. Okay. Okay, I hope this is clear to all of you. So now let's move on to discuss the next problem. Problem B. So B states as follow that limit sequence is nothing but 1 over minus 1 to the power n divided by n plus 2. Okay. So my xn is this. So my so by looking at the pattern of the sequences, uh, just writing down the first n terms or something like that, you can guess that this sequence converges to zero. Okay, um, because it has denominator which is n plus 2, and as n goes to infinity, as you take higher and larger value for n, this denominator is going to dominate in the sequence, in which means that for larger values of n, your sequence xn will be very close to 0. Okay. So uh, I claim that this xn converges to 0 as n tends to infinity. Okay. So how do we prove that? Again, in order to prove that, I go back to the definition of uh, epsilon, definition of sequence convergence. So if I start with, for a given epsilon, I need to find out n. So what I have given, that this is smaller than epsilon. I need to find out n for which this sequences are going to be, the tail of the sequence is going to be smaller than epsilon. So which is same to say that minus 1 over n divided by n plus 2, this thing is smaller than epsilon. Okay. Now since I'm taking the modulus, so 1 over minus 1 to the power n just become 1. So it is 1 over n plus 2, this modulus by 2. And now we know that this thing this thing is smaller than 1 over n. Okay. Why? Because n is smaller than n plus 2, implying 1 over n plus 2 is smaller than 1 over n. Okay. And we know that 1 over n is smaller than epsilon for there exists some n. So we can use that for n greater than some n naught. Okay. So this completes the proof. So thus okay. So now let's discuss the C part. Um, Again, my action sequence is nothing but this. Okay. So I can take now I need to use the fact that 1 over n is 0 whenever, so the sequence 1 over n is 0 always. Okay. So I need to use the fact that sequence 1 over n is 0. So how do we uh, so we need to convert this expression of sequence into something and into a sequence which looks like 1 over n type. So how do we do that? So we take square root of n common in the numerator, so we will get 1 over this. Similarly, I take square root of n common in the denominator, so I will get this. Okay. So yeah, now I can cut these two values. Is square root of n, I can cut it from cut square root of n from numerator and denominator. So I will get, I have reduced my sequence into a sequence which looks like this. Okay. Now I state another fact which I have proved, uh, which I haven't proved, but it's a fact. You can find it in any standard real analysis textbook, that Yeah. uh, Multiplication and non-zero division of two sequences xn, yn is of two convergent sequences is again a convergent sequence with convergent sequence, and if xn converges to x and yn converges to y as n tends to infinity, their product gonna converge to this, and okay. So I'm gonna use this fact in order to prove this. So how do we use? So we know that the individual sequence, so individual numerator sequence is converging to one. Similarly, individual denominator sequence is again converging to one. So their division is also going to converge. And second thing is that the denominator is always non-zero. Okay, for any given natural value n, the denominator is always taking non-zero values. So what I'm saying is that 1 minus 1 over n is always non-zero for all n in natural numbers. Okay, so I can apply this result, this fact. Okay, so what will I get? So I will get the limit will be nothing but of this divided by limit of this, which is 1 over 1, which is 1. Okay, so the limit of this thing will be 1. So this completes the proof of the C part. Okay, now let's move on to D part. This is the question. N plus 1. Okay, put the other way. Okay, so um, yeah. So again, we use the facts that sum of sequences, sum of uh, convergent sequence again convergent, sum of division of two convergent sequence again convergent sequence, multiplication of two convergent sequence again convergent sequence. We will use that fact. So first we need to simplify this thing. So how do we simplify this? So you can rewrite this expression as this, correct? Now the first uh, now the first expression will give you 1 over square root of n, and the second expression will give you n to the power 3 by 2. In other words, you can take square root of n common and you will get 1 plus 1 over n. Okay, so now we use the fact that now we consider the first one to be one sequence, call it yn, second one to be the sequence zn. Okay, and this is my xn term. Now yn, which is this, converges to 0 as n tends to infinity. Similarly, Zn, which is 1 plus 1 over n, it converges to 1 as n tends to infinity. So here, in order to prove that this converges to one, I am using that sum of convergent is uh, convergent sequence, and the limit is nothing but going to be the limit of the first sequence plus the limit of the second sequence. Here I'm using the fact that 1 over square root of n is converge is 0 u. So yeah, so I'm using the fact that limit of 1 over square root of n is 0 as n tends to 0, as n tends to infinity. Now the product of these two things, uh, so limit of 1 over square root of n plus 1 over 1 plus n will be limit of 1 over square root of n product limit of 1 plus 1 over n. So first thing is 0 times 1 going to be 0. So limit of this sequence is 0. Okay. So this completes. So these were the problems that I had in mind to discuss with you on the sequences, their convergence, and how do we solve problems on the convergence of sequences. Okay. So this completes the first part of the today's discussion. Now we move on to discuss the topology on real number lines. So before that, if you have any questions, you can ask me. Okay, so let's move on to discuss more questions on topology. So by mean topology, we mean that the open sets of the real number line and the closed sets of real number line, and what are the neighborhoods of a point, what is the limit point of a sequence, or what is the limit point of a set, a subset of a real line, and so on and so forth. So these are all part of the discussion on topology. Okay, so we are not explicitly uh, defining topology, we are not discussing explicitly the general definitions of closed set and open set. We will be sticking ourselves to the real line, and we will be using the definitions that are uh, that works in the case of the real line. Okay, so uh, before we further start, let me start with discussing the closed set. So let us recall what do we mean by a closed set. So we define the closed set to be, there are multiple definitions. So one of the definition is that complement of a of an open set in R. Another definition is um, set A. A set A is called closed if it contains all of its limit point. Okay. And now what do we mean by limit point? So we know a limit point of a sequence. Okay. Uh, a subset or a set of a set which is subset of R is called closed. Yeah, if it contains all of its limit point. So we know a limit point of a sequence. Okay. So, so how do we define a limit point of a set? So we define a limit point of a set to be uh, you you can consider a sequence on that set, which is a convergent sequence, and you look its limit of that sequence, and that limit will be the limit point of that one of the limit point of the sequence. Okay. So I have discussed these things in my previous discussion session, but just to give a quick recall about this part, let me say it again. Mm. So yeah, so we have defined sequences for any arbitrary subset of R as well. You can have a sequence on any arbitrary subset of R. So let's say this is your sequence Xn that you have defined, and this is a convergent sequence. So since it's a convergent, so as n tends to infinity, you will get some limit point of Xn. Okay, so you will get some limit point of the sequence Xn. So this X is called a limit point of A. Okay. So for example, if I consider this set 1 over n, so what is my set? So my set X uh, in R, where X is looking like 1 over n for all n in natural number set. So if I call this set to be A, so what is a limit point of this set? So limit point of this set is, you all clearly know, is 0. So 0 is a limit point of A. Okay. So yeah, so limit point of the set A. Similarly, if you consider, so this is one example. Another example is if you consider this set which is 0 comma 1, open interval 0 comma 1. So it's basically considered is, so it contains all X in R, which lies between 1 and 0, but it doesn't contain the endpoints, which is 0 and 1. So 0 and 1 are the limit points of P. Why? Because you can always consider this sequence, which is 1 over n. Okay, so this sequence converges to 0. Okay, and these 1 over n, these sequences are contained in B. Similarly, you can consider this sequence as well, which is 1 minus 1 over n, and from varying in this converges to 1, and this sequence by n is contained inside B. Okay, so so limit points of B are 0 and 1, correct? Because there are sequences on B, there is a sequence on B which converges to 0 and 1. So 0 and 1 are the limit points of B. I hope it's clear to you. And now, what is a closed set? Closed set is nothing but which contains all of its limit points. So, as per the discussion, if I look into the first example, so A doesn't contain the limit point because the elements of A are nothing but 1 over n type. So A doesn't contain the limit point. So A is not a closed set by our definition. Okay, because it leaves out a limit point. Similarly, the second example where B is an open interval 0, 1, it also doesn't contain any of its, it also doesn't contain its limit point, which is it leaves out 0, it also leaves out 1. So 0 and 1 are two limit points of B, and B doesn't contain either of them. So B is also not a closed set. Okay, so I hope this discussion is clear to all of you. Now we come back to the question, which is state whether true or false. The set Z, the set of all integers in R is closed. So we prove this uh, by understanding the limit, by understanding the sequences which are possible in this case. Okay. So if you think of a sequence xn, let xn be a sequence in z. Okay. and and moreover xn is a convergent sequence, because we are looking for the limit point, so we need to start with a convergent sequence. Okay, so we start with a convergent sequence in z. Yeah. So now, uh, now I want to say, I claim that xn is a, a constant sequence after a few finite terms, after the first few, after first few finite terms. So what do I mean by that? If I after finite many terms, the sequence with the remaining sequence, which we also call the tail of the sequence, okay, is are nothing but a constant sequence. So okay, so yeah, so we want to say that it is a constant sequence after uh, first few terms. So for that, we just need to understand the definition of a convergent sequence. Okay, so since so we assume that let xn converges to x as n tends to infinity. Okay, so now this, so for epsilon greater than 0, there is some x, there is an n in natural numbers such that xn minus x is smaller than epsilon for all n greater than n. Okay, now this x is again going to be some uh, yes. So we assume that x is some real number. Okay, so we assume that x is some real number where it is converging, uh, and now xn is what? So xn are the terms of z. So yeah, so if I look into this x, neighborhood of x, which is a real number. Okay, so if I so what do I mean by this? This means that I'm looking into the epsilon radius neighborhood of x centered at x. Okay, and it contains all integers which is larger than and in this sequence. Okay, so so if I draw this real line, okay, and if I try to draw this, let's say this is my x, this is my point x, and these are the integers. So this x will be sitting between any two integers. So this x, we assume it's sitting between two integers, let's say a and b. Okay, we can always assume that. So either it's going to be equal to them, or it's going to be it's going to be integer, or if it's not an integer, so it's going to be sitting between two integers. You can always find out an integer which is larger than that, and this is because of something which we called the RK median property of of real numbers. Excuse me. Yeah. So we can always say that it is going to lie between two integers. Okay. So I'm saying this is my A. In our case, if in my drawing it is A and this is B. So it is sitting between these two. Now, if you choose a small enough radius epsilon, okay, so I'm going to choose uh, some epsilon which is smaller than 1. Okay, or let's say the distance between these two integers. Sorry. So if I choose, so I have these two numbers, that means b minus x and x minus a. Okay, so I consider the minimum of that, call it to be m, and I take epsilon to be smaller than m. Okay, so if I do that, I will get a smaller neighborhood of this thing like this. This is my epsilon neighborhood. Uh, okay, which does not contain any integer. Okay, so it doesn't contain any integer. So if x is a real number and not an integer, then I can always find out a small enough uh, I can always find out two integers where it is going to be bounded above and bounded below by Archimedean property, and I can always find out a small neighborhood of that uh, uh, x, so that a small neighborhood of x, so that it doesn't contain any of the integer. Okay, so it implies that this limiting x has to be z, has to be the integer, it has to be one of the integer. Okay, so if it is going to be an integer, so now if so it reduces to this case that um, so x can't be a real which is not sitting inside z. So if we assume that if x is an integer, so and then again I draw the real number line. So this is my x, this is now x minus 1, this is x plus 1. Okay, so now this x is an integer now, so and so forth. Okay, so and I'm looking limit a convergent sequence. Okay, so in other words, if I can find out, yeah, so for any small enough neighborhood of this, okay, for any epsilon, for any epsilon, uh, for any epsilon neighborhood of this x integer, I will be able to find out the other uh, numbers of the sequences. Okay, but as you can see, uh, I have chosen a small enough x, which is I have chosen epsilon which is smaller than strictly smaller than 1. Okay, so if I do that, I cannot. So there is no integer. Uh, so the only integer, so only integer xn which that lies in the neighborhood x minus epsilon x plus epsilon is x only. Okay, so in order to so so this implies, so to xn to converge to x as n tends to infinity. Okay, uh, the tail of xn needs to be just a constant sequence, needs to be a constant sequence. Okay, so more specifically, if I have just written it mathematically, so for epsilon smaller than 1, this condition, the last condition, it forces us that this xn cannot be any other integer than x. So uh, so so after this, so for all n greater than uh, this capital N, all xn's are going to be the constant n, and in other words, the constant sequence, it will, so for any given sequence in z is going to be, any given converted sequence in z has to be a constant sequence eventually. Okay,
Sir,
okay, so
how? Hello, sir. How the
now
figure would look
from
like?
that part, we can say that so every limit point of of z is going to be inside z only, because if I take any sequence, any converted sequence, it is eventually becoming the constant sequence. So how would the figure be look like? Are you referring to this figure? Yeah, so this is the figure that, because in the case, so in the previous case I have proved that the limit point of the of a sequence, which sequence of integer sequence can't be a real number other than integer. Okay, so this is the proof for that. And now the second part, when I assume that the limit point of the integral sequence is going to be an integer, so in that case you can always, for epsilon smaller than 1, there is no other integer than x, than the limit point which contains in that sequence, which contains in that neighborhood. So for n greater than equal to some uh, n, all the values in the sequence has to be the limit point x. So it proves that uh, the all the limit points of z are in z, implying z is a closed subset of R. Okay, so I hope this is clear. Now we can move on to the next question.
Yeah, hello, sir. Hello.
Okay, so now next question is that state whether or not, whether true or false, there are no subset which are neither bounded below nor bounded above. Okay, so I have already discussed what is bounded below and what is bounded above in my previous discussion session. So just to give a quick recall, um, so we say a set is bounded below. Yeah, so we say a is set A is bounded below if there is a real number B in R such that B bounds such that any every element of A is larger than B. Okay, they can be equal also for all A in A. Similarly, we say a set. Similarly, we say a set A is bounded above if there is an element U in R such that every element of A is smaller than U. Okay, so bounded below, bounded above. In okay, so uh, okay, I will tell you the greatest upper bound, lower bound as well. Uh, so for example, if I draw a figure, if I draw the line, real line. Okay, so let me draw the real line, and my set is and my set is something uh, like this set 3 4 5. It consists of only three elements. So let me draw those element 3 4 and 5, 2 6 1 7 and so forth. So on this real line, this is my set. These 3 points are in my A. So can you tell me an element which is bounding, uh, uh, which is larger than every element of A? Can you tell me an element which is larger than every element of A, larger or equal to also? So 6, correct. So now my question you will be is 5 uh, 5 upper bound of A. In other words, is A bounded above by 5? So these are two same questions. Okay. So is A bounded above by 5? So we go back to the definition of bounded above. So we say a set is bounded above if there is an element U in R such that every element is either equal to U or smaller than. It can be equal also. Okay, not for all element in A, but that element can be equal to some element of A. Okay, and it can be and it has to be larger than other elements. So either of the, so this it needs to satisfy. So does 5 satisfy this property? Yes, 5 does satisfy the property. So because if you take any element, so 3 is smaller than 5, 4 is smaller than 5, 5 is equal to 5. Okay. So in other words, every element is either smaller than or equal to 5. Okay. So 5 is a 5 bounds A. Okay. 5 bounds A. Now if I go back to the definition of this, uh, so we say a set is bounded below by some element. So this element is called the lower bound of A. Similarly, this element is called the upper bound of A. Okay. So 5 is an upper bound of this set A. Similarly, I can ask a similar question: Is 3 and is 3 a lower bound of A? So as you correctly pointed out, it is a lower bound of A. Okay. Now, what is now you ask me a different question. What is supremum and infimum of a set? So you can so so if I make a table like thing and say lower bound of A. If I make a table like this and I make this table in such a way that um, so I'm making this table lower bound of A. So what are the lower bound, and I'm writing the numbers in a decreasing order. Okay, what do I mean by that? So we know 3 is a lower bound of A. Now any number smaller than 3 is also a lower bound. Okay, so any number, so 2 is also a lower bound, 1 is also a lower bound, 0 also a lower bound of A. Okay, but can you find out an element which is larger than 3 and lower bound of A? So in other words, does there exist any element which I can write on top of 3? The answer is no. I cannot find out an element which is larger than 3 and lower bound of A. Okay, so in some sense, uh, A, so in some sense, 3 is in some sense greatest among all the others lower bound. Okay, so 3 is larger than any other lower bound of A. Correct. Similarly, if I say for upper bound and I start writing a table, I start entering the values in an increasing order. So I write the lowest value on the top, which is 5, and then 6, and then 7, 8, and 9. Okay, so can you tell me, so is there any element which is an upper bound of A and smaller than 5? So answer is no. There is no element this which is uh, which is larger than which is smaller than 5 and upper bound of A. So these are special elements. Okay, so we call this element to be the greatest lower bound, to be the infimum of A, and 5 is what? 5 is the smallest lower bound. Sorry, 5 is the smallest upper bound. So it is called the least upper bound uh, in that way, which is nothing but supremum of A. Okay. So for some exercise, like you can tell me uh, what is the supremum and infimum of this set A, or greatest lower bound and least upper bound. No, it is bounded above and bounded below. Okay, so there is greatest lower bound, greatest upper bound to this. So okay, so uh, So is 0 a lower bound of A? Is 0 a lower bound of A? So you just need to check that whether it satisfies the property or not. That it needs to be smaller than every element of A. So it is by definition uh, a lower bound. Because what is the definition of this interval? This interval consists of all elements in X, which is between 0 and 1. Okay. So every element of X, every element of A, so every element of A is larger than 0 and smaller than 1. So this is true. So 0 is a lower bound of this set. Okay. Now I claim that there is, now in order to prove that 0 is a greatest lower bound, I need to say, correct, 0 is the infimum, supremum is 1. But that is your guess. Okay. You need to also prove mathematically why 0 is a lower bound and 1 is a upper bound of, a least upper bound of this set. So in order to say in order to prove mathematically, you need to say that there is no lower bound which is larger than this lower bound. Okay, then it will be the greatest lower bound. Okay, so you need to prove that there is no lower bound of A larger than, this can't be proved using the epsilon delta definition. So this is not limit. This is not sequence. This is upper bound lower bound. So this can't be proved using epsilon delta. Epsilon delta comes in when you prove uh, continuity or limit, then the epsilon delta comes in. Okay, so there is no so there is no lower bound of A larger than 0. So how do we prove that? Suppose there is. So I want to prove this part. Okay, the part which is written in blue, and I assuming the negation of that. Uh, suppose there is a lower bound B in R such that B is larger than 0 and B is smaller than any other element for all A. Okay. So now, uh, by definition of open interval 0 comma 1, B will be an element of 0 comma 1. Correct. First of all, by definition, because it is larger than 0, so it has to be an element of 0 comma 1. Now, a second thing, that can I find a smaller element of 0 comma 1, open 0 comma 1, which is smaller than B? Yes, I can find out. Just consider this element, which is um, yeah, I can consider uh, 0 plus, I can consider B by 2. Okay, so B by 2 is an element which is smaller than B. Okay, and B by 2 will be larger than B because B by 2 is still a positive number. Okay, so B by 2 is smaller than B, but it is larger than 0. Okay, so B by 2 is in 0 comma 1 and it is smaller than B, so it contradicts the assumption that B is a lower bound. Okay, so so B is not a lower bound. In other words, you cannot find. So in other words, there is no lower bound of A. So in other words, there is no lower bound of A which is larger than 0. Okay, so this is how you prove this thing, that the lowest, that 0 is the greatest lower bound or infimum, and 1 is the, similarly you can give an argument for that 1 is the greatest upper bound, sorry, least upper bound of that set A. Okay, now I come back to the question which was originally asked, that there is no subset which are neither bounded below nor bounded above. Okay, so it asks you to say that whether it is true or false, that there is no subset which are neither bounded below nor bounded above. And the answer is yes, it is true. Sorry, it is true. Um, yeah. So in other words, this sentence can also be think of as there are subset which are either bounded below or bounded above. Okay, because there are two negations. Negation is coming twice in this statement, so you can say that there are subset. This statement is also, this is also equivalent to say that there are subsets which are either bounded below or bounded above. Correct, you correctly pointed out. So yeah, there are subsets which are either bounded below. Yeah. No, the question asks you. The question is asking you that. Question is saying you need to state whether this statement is true or not. Okay, so what is the statement? The statement is that there is there are no subset which are neither bounded below nor bounded above, which means you cannot find out any subset. Why is it false?
Uh, uh, Hello, sir.
Can you give me an example of a subset which is not bounded below and bounded and not bounded above? So if you are saying that it is a false statement, that means you need to come up with with an example, or you need to come up with a subset which is not bounded below and not bounded above. Yeah. So basically, uh, you are not going to see, you are not going to the complex numbers. You are just only because bounded below doesn't make sense in the complex number. Bounded below and bounded out doesn't make sense in complex terminology, because we only have order topology. You need to define a so there is something called order topology. You know, to define order in C, then you can talk about the bounded below, bounded above. So you are only in R, real number line. You correctly pointed out that is, you can take R is also a subset of R. Okay, instead of saying it C, you can say that R is a subset of R. But I can again modify this question by asking you that what are is there any proper subset which is bounded below or bound not, which are neither bounded below or bounded above? So there is no proper subset. Okay. uh, oh yes, yeah, correct, correct. Yeah, yeah, you are correctly right. Yes, yes. So Z is a proper subset, and Z is neither bounded below nor bounded above. That's so. What are the examples? Z, Q. Uh, yeah, these are the examples. Z and Q are the examples which are uh, neither bounded below nor bounded above, and they are also proper subsets. So this statement is false. Correct. Very good. Yeah. Okay. Okay. So you're saying this statement is true, that every subset of R which is countable and compact must be finite. So what is the definition of compact that we are assuming? So let me first recall the definition of compactness, then we will discuss the question. So in R we say a set A is compact if it is bounded and closed. Okay. So more specifically, a set A in R is compact if it is bounded and closed. Okay. And what is countable? So we say a set A is countable if there is a bijection F from natural number set to A. Okay. So yeah. Yeah. So this statement is actually false. Okay. It is not true statement. And I will also give you an example why it is true. Uh, sorry, why it is false. I will give you an example why it is false. So it is not a true statement. So so what you need to so you need to consider a subset. You need to consider a subset of R which is countable and compact and not finite. Okay, so you need to construct a subset which is not finite, countable, and compact. Okay, so can you construct such a set? So in other words, what do we mean by compact? It needs to be closed also. So basically, all the limit point needs to be part of that set, and it needs to be bounded also. So you need to find out. You can always find out its upper bound and lower bound. So it needs to be bounded. Okay. So yeah. So bounded means so as A is said to be bounded if it is if it is upper and lower bounded. Okay. So I'm not aware of what box function is, but I can give you a function which is much simpler to understand. Like I find that simple function. So if you so you need to not come up with a function. You need to come up with an example of a set. Don't need to come up with a function. Okay. So if you consider this set, which is 1 over n union with 0. Okay. So it is a countable set. So is a countable. Now second part, is a bounded? Third question, is a closed? And fourth is a not finite? So clearly it is not finite because it is yeah. So it is bounded, correct? Because what are the bounds? It is bounded below by 0. Okay, basically the infimum of a is 0 and supremum of a is 1. So it is bounded. Is it closed? Yes, because it contains all of its limit point. What is the limit point of a? So limit points of A is 0, so it contains it. So it is also true. Is it not finite? Yes, it is not finite because it contains infinitely many terms. So so this is also true. Yes. And is it countable? Yes, it is countable because you can give a bijection from n to this. So you can give n to A, n going to 1 over n, okay, or n plus 1, and where will the 1 go? And 1 will go to for n not equal to 1, and 1 will go to 0. Okay. So this will be 1 to 1, sorry, n minus 1. Yeah. So this will be 1 to 1 correspondence. It's a bijective map, so it is countable. So it is countable. So it is satisfying all four properties. So there exists a set which is countable, which is compact, but it is not finite. So this statement is false. Okay, is it clear? Oh, countable not. So, so for countability, you need to define a map from natural number set to. You need to give a bijection from natural number set to A. Okay. So you define this map carefully. So you just say that for f of 1 is 0. Okay, and f of n, or in particular you say that f of n is 0 if n is equal to 1, and if n is not equal to 1, okay, or greater than equal to 1, I define it to be 1 minus 1 over 1 minus n. Okay, so so this will include the 0 singleton, and this lower part will include 1 over n. Okay, so in this way you have mapped every element of A bijectively from n, and this is a bijection. You can check this is a bijection. Okay, and this is a bijection from n to A, so this is implies that A is countable. Is it still clear, or there is some doubt? I think you are having doubt in this second part. So what I'm doing, I can explain it more simpler. What I'm doing is, so you have uh, you want to list out the value. So first place is the first place, second place, third place, fourth place, sixth
Hello,
place,
sir.
and so on. So you want to now put elements of A in these places. So by definition, I'm putting 0 on the first place. And now what is n equal to 2? F2 is what? 1 over 2 minus 1, which is 1. 1. What is 3? N equal to 3. It is half. Then 1 over 3, 1 over 4, 1 over 5. Yeah, you can speak. You can unmute yourself and you can speak.
Yeah. Hello, sir. Hello, hello, sir.
I can't hear you if you are saying something. Okay, it's fine. Are you able to understand what I'm trying to convey? Yeah, yeah. So, so I have places where I can where I can insert the values of A. So in the first place, I'm inserting 0. Second place, I'm inserting 2 and 3 at half. So you can see that from 2 onwards, 1 over n sequence will get uh, inserted completely. And on the first place, I'm just inserting this singleton 0. Okay, so because this is my set, 1 over n union singleton 0. So that's how I'm inserting values in it. So this proves it. It is countable set. It is a countable set. It is a compact set. and it is not finite. So this statement is false. Is it clear? Okay, okay, good. Yeah, so then this next question uh, is saying that again it's a true false, and you need to say that if a subset of R is open and closed, then it has to be an interval. So this is again false. Okay, and the argument is simple, because if you assume that A is open, what do we mean by that? So I let me recall the definition of A. So a subset of R, is said to be open if for each A in A, for each element in A, there exists a epsilon radius neighborhood centered at A, which also be denoted by this ball of epsilon radius centered at A, which is contained inside A. So what do I mean by that? I mean simply that if you think of real line, and this is your point, this is your subset A, and this is your point A in that subset. So you can always able to find out a epsilon radius neighborhood, uh, okay, which is completely sitting inside. So this is centered, and this radius is epsilon. Okay, so which is completely sitting inside A. So this is called B epsilon of A, and it is completely sitting inside A. And this happens for all A, for all elements in A. Okay, if this happens for all elements in A, we say it is an open set. Okay, and now second thing is close. We already know what close is. That all its limit point needs to be contained inside this. Okay, so now it is saying that if a subset is open and closed at the same time, then it has to be an interval. So it is a false statement, because yes, all limit points needs to be inside of that set. Yeah. So and there is also one more fact. I don't know whether you guys know or not, but you can treat it as a fact. I don't know whether I should say it or not. Yeah. No, no. I'm just saying that uh, yeah, complement of a open set is closed, and complement of a closed set is open. So if A is open, then R minus A is closed, and A is closed, then R minus A is open. Okay. So if I use the second fact, so A is open, implying that R minus A is closed, and A is also closed, which is uh, or in other words, if I start with that A is closed, then this is an open subset, and similarly this is also an open subset. Okay, and we know that R minus A union A is gives you complete R. Okay, yeah. So it implies that R minus A must intersect with A. This has to be non-empty. This intersection has to be non-empty. So in other words, what I'm doing is, if you just draw the real line, okay, so you can think of that, if this is my A, okay, and what will be the R minus A? R minus A will be this thing, this whole part which is outside of it. Okay, so and now if you union them, if you unite them, you will get R as of whole. Okay, but it says that uh, now but this implies that their intersection needs to be empty, their intersection needs to be non-empty. Okay, because their union is whole of R, both of the sets are open, so they can't contain the limit point, they can't contain this limit point. Okay, so they can't contain this and this limit point, either of them can't contain limit point, so their intersection has to be non-empty. Okay, because their union is equal to R, so their intersection of both of the sets has to be non-empty, which is not going to be the case, because uh, by definition R minus A intersection A is empty. Okay, so if I assume these two things, that their union is equal to R and their intersection is empty, which is by definition of the complement, then it says that that A is not closed. Why is that so? Because there will be some points which will be left out, because R minus A is again is also open. So where this R minus A is ending, the endpoints of R minus A, which are also not contained in A, uh, so they are not, so they are, which are the limit points of R minus A, and limit points of A are going to match, and they are and now because A is closed, so it needs to be contained inside A as well, but it gives you a partition of R. They can be close at the same time, but their intersection then uh, so if you assume that if A is closed, then its complement has to be open. Okay, if you assume that A is closed, then its complement has to be open, but you are also given that A is open. So in other words, you are getting two open sets. Okay, you are getting two open sets whose union is equal to R and whose intersection is equal to empty set. Okay, so in other words, it is giving you a partition of R. So you are breaking R into two parts, which is not possible because R is a connected set. So okay, I leave this exercise because it is going beyond the scope of this course, I suppose. So I'm leaving this exercise. It is, I'm finding it difficult to explain it to you. So I'm leaving this exercise, but this statement is false. I will discuss this exercise if I find uh, a simpler solution to this exercise next time. Okay, so we discuss this question number 5 then. Let A be a non-empty subset of R and P is in R such that P is the only limit point of A and P doesn't include in A. Okay, so P is only limit point of A and P is not in A. So what can you say about A? Is it open? A is open. No, A is not open. Why? Because then the only limit point assumption will be broken. So what happens if it is A is open? So you can find out an element in A such that, so if A is open, so you can find out a neighborhood, epsilon delta neighborhood of A, this neighborhood, okay, epsilon delta neighborhood which is contained inside A. So there will be some B of A which is contained inside A. Now you can consider a sequence in this, which sequence like this sequence, A minus 1 over A, which is inside B epsilon of A, and this will be converging to A. So A will be then limit point of A, but it is given that B is the only limit point which is lying outside of A. So A can't be, but A is sitting inside, small a is sitting inside A. So A can't be open. Okay, because if it is open, then you can always find out a limit point which is sitting inside A, which is not true. Okay, now is A closed? A is not closed because the limit point is not belongs to A. So A is not closed because the limit point of A doesn't contain inside A. So it is not closed. A is both open and closed? No, because neither A and B true, so it is not true. So option D is correct. That A is neither open nor closed. Is this clear? Okay, good. So I stop at this point. Uh, so you can, if you want, you can attend my next session also, same time Monday. Okay, the meeting link is, let me share the meeting link with you so you can attend um, next time also. Yeah, so this will be my meeting link. I will be taking discussion session next Monday as well, same time from 7 o'clock to 9 o'clock. Okay, and if you find sessions useful, you can, I suggest you to strongly suggest you to attend these sessions.